Hey guys, welcome. Yeah, so I hope everyone out there is well and safe. And here's the third installment on additional problems on vectors, and we've got a really cool one here. So we've got this plane here whose equation is given, and what we have to do is find the equation of two other planes that are 2 units from this plane and parallel to it. Now, if there are 2 units from this plane, they must be parallel to it, right? You can't be adjacent to a plane. But yeah, let's get on with this. Okay, to start, let's say that we've got that plane and then this plane and this other plane. So these are the three planes, right? And let's say that the plane whose equation is given is this one. So then we've got two planes that are parallel to it, one 2 units above it and the other 2 units below it. Now, I have very well made videos on vectors and then concluding that series with equations of planes. And so basically, I have videos dedicated to the vector equation of planes. So I'm not going to talk about things that I said in those videos again here. So watch those videos if you need basics on the equation of planes. But what we said in one of those videos is that what we do is we take any random point xyz on a plane and connect it to a specific point that we know is on that plane, say x0, y0, z0. So we're going to do the same on all three of these planes and construct what's called the x vector, right? So the x vector is a vector that you know is on your plane. Again, the way you construct this x vector is by taking a specific point that you know is on your plane, namely x0, y0, z0, and then the other endpoint of that vector being any generic xyz. So since we don't know what xyz is ahead of time, we just call it xyz. And so by taking this end xyz and the specific point x0, y0, z0, we construct the vector x, which, you know, if we construct it so that the arrows on this end, the vector x would have to be the following, which is x minus x0, y minus y0, and then z minus z0, right? Okay, cool. Now, we know that the way we determine the inclination of a plane, that is basically the slope of the plane, so to speak, is by what's called the normal vector. So only one vector can be perpendicular to a plane, up to scalar multiples. And so then the way we identify a specific plane uniquely as far as its inclination is by saying what vector is perpendicular to it. That is, what vector is normal to it. Remember, normal and perpendicular are synonymous words. Okay, so this vector we call the n vector. As you can see, in each case has to be perpendicular to the x vector. Also, more importantly, in this specific question, this n vector is the same in all three of these planes. That's because the three planes are parallel. If they're parallel, their inclinations must be the same, and therefore the normal vector that identifies them must be the same. Yes, technically we can say that this n vector is some scalar multiple of this n vector, but why get fancy? We can just use the same n vector in all three cases. So when we write the equation of the two other planes, we're going to use the same n vector. All right. Now, this n vector is usually written as ABC as far as x, y, and z components. So let's state a convention. But as we said, since this n vector has to be perpendicular to the x vector, we know that perpendicular vectors have dot products equal to 0. So what we can say is n dot x is equal to 0. This is what we call the vector equation of a plane, right? Now, you're going, wait, there is no dot product in this equation of the plane. What does that got to do with this? Well, if you watched those earlier videos, you wouldn't be asking silly questions like that. But we know what the dot product is, right? So the dot product of n and x would be like multiply corresponding entries. So a times x minus x0, b times y minus y0, and c times z minus z0, and then add them up, right? That's what the dot product is. So if we do precisely what I just said, then n dot x is going to look like this, right? And we've got n dot x is equal to 0, so we set it equal to 0. Now, if we distribute the a, the b, and the c, notice that a times negative x0, that's just a constant, and b times negative y0, that's a constant. C times negative z0 is a constant. So what I'm saying is we'd get ax plus by plus cz and then plus a constant equals 0. If we take the constant to the other side, we get exactly this equation. That means that a, b, and c, the coefficients of x, y, and z, are exactly where we get the n vector from. What I'm saying is distribute the a, b, and c in these parts, then collect all the constants and take them to the other side. What you'll have on the left side will look exactly like this. And so then a, b, and c, the components of the normal vector is just the coefficients of x, y, and z. And so that's 2, negative 3, and 4. So what I'm saying is the n vector for our main guy, this, we can easily get from its equation. And so we see that the n vector is, and I was just showing you everything I had already said. The n vector ABC is just 2, negative 3, and 4. Got it. And since we said that we're going to use the same n vector in all three cases, we're using 2, negative 3, and 4 for that plane and this other plane. Got it. So then we see that the only difference in the equation of the three planes is going to be on the coordinates x0, y0, z0. But wait, we don't even know x0, y0, z0 for this guy, let alone the other guys. So how could we first of all find x0, y0, z0 for this guy? Because if we can find x0, y0, z0 for this guy, what we can do is add 2 to x0, y0, z0, z coordinate only. We can add 2 to just the z coordinate to find the x0, y0, z0 for this guy. And for this other guy, we can subtract 2 from the z coordinate of x0, y0, z0 in this guy. Now, again, how do we find x0, y0, z0, the specific point on this first plane to begin with? We can do it very cheaply. We can just assign values to x and y and say we claim that they're both equal to 0, because there's nothing special about x0, y0, z0. The only thing special about it is that it is a specific point we know on our plane. So for that, as I just said, we could just assign x and y values and then figure out what the corresponding z value has to be to make the equation true, and that will mean that we found a point on our plane, and that's all we care for, because again, x0, y0, z0 is just a point on our plane. Again, question mark, how do we do that? Well, we take the equation and let x and y say equal 0. We could have let x and y equal any two other numbers we'd like, but why not use 0 since we could do that? Then the equation would turn into the equation of the plane, would turn into this, right? Okay, and so then that would mean that z is equal to 3. So we know that a specific point x0, y0, z0 on our first plane, the plane whose equation we're given, is 0, 0, and then 3. Fine, as I said, since these two other planes are 2 units away from this plane, well, we could just add 2 and subtract 2 from the z coordinate of this point, which we know is on this plane. And so adding 2 and subtracting 2 from the z coordinate of this point is going to get us 2 other points on the 2 other planes. And so it's going to give us x0 and y0, z0 for the 2 other planes is what I'm saying. So, you know, we can say that this other one is the one that is 2 higher, and this other one is the one that is 2 lower. And so there it is. And so then now we can easily see that the equation of the 2 other planes, which is what we're after, let's call them planes A, B, and C. So for plane B, we've got the n vector is that, so we go n dot the x vector. The x vector is x minus x0, which is x minus 0, y minus y0, which is y minus 0, z minus z0, which is z minus 5 for the blue plane. And so n dot x equals 0, right? And then for finally this, I suppose, tan plane, we've got the same n vector as we said. The only difference is the x0, y0, z0, which this time is going to look like that, right? Okay, cool. And so again, n dot x equals 0, and there we are. Obviously, you can, using the dot product, turn these two equations to look like that, but you know, that's extra, more than what you should ask of me. I hope you enjoyed this. Lots more to come. Keep watching. Take care.